Thank you very much, Archie and Blake. Stand away from that a little bit. Great pleasure to be here. I've got to tell you right now, I'm going to stick around through the break after my talk. People that would like to come up and talk to me about what I've said, ideas. I'm really pleased to speak to this group because, quite frankly, we need more farmers who are willing to look at these problems and try to come up with solutions because we don't have all the answers. I'm going to tell you what we do know. I'm sure I'm going to get a lot of questions and I'll answer as many as I can. I'll give you inferences when I'm not sure of an answer, or I'll tell you if we have research underway, and there's a lot of research on this right now. But we need people who are willing to experiment on best management practices and to try those and to evaluate them. You'll see that more from the talk. Again, I feel like I'm probably preaching to the choir here. This group is the people who are willing to make those tough decisions and try to innovate on their own farm, and we need more people like you guys. All right, so let me see if I can make this work. As Archie indicated, I'm the past director of Stone Lab. I started up here in 1971 as a grad student. This Gibraltar Island, you see, this is at Put-in-Bay. Put-in-Bay is where, or the town that's located on South Bass Island to the west of, say, Pelee Island, Canada. So Gibraltar Island's about 5 miles from the US-Canadian border. That's our lab in the foreground, our research building in the background. This is the oldest freshwater biological field station in the country. I'm also the past president of the National Association of Marine Labs. So when we go around the country, there are over 140 marine labs like Scripps Institute out at La Jolla or Woods Hole in Massachusetts, on the Great Lakes at Stone Laboratory. We've been in this location since 1925. The lab started in 1895. We do a combination of research, education, and outreach. We're one of 33 programs in the country. We're part of NOAA, National Oceanic and Atmospheric Administration. We're centered at Ohio State University. We try to involve all the universities in Ohio. We try to provide leadership and also partner with universities all over the country, including on the Canadian side. The reason I have to leave after the break is I'm hosting or co-hosting a conference at University of Windsor, and I have to speak at 1 o'clock at the University of Windsor. We get about 30,000 visitors out here. Put-in-Bay gets about 1 million tourists per year. So the images that I'm going to show you up at Put-in-Bay are not things that are hidden. These are things that lots of people see and encounter. 7 extension agents. We're one of the top programs in the country. We're one of the co-hosts of the Lake Erie Millennium Network. This was a group that we saw that if we're going to manage Lake Erie, if we're going to do research on Lake Erie, we've got to do it collaboratively, binationally, US and Canada, Ontario, Ohio, Michigan, Indiana, Pennsylvania, New York. We've got to all work together on this. When we formed the Lake Erie Millennium Network, we put together 4 chairs. We wanted to have these co-chairs represent academia. So I'm the U.S. co-chair representing academia. Jan Siborowski at University of Windsor is the U.S. or the Canadian co-chair recommending as part of academia. On the federal agency side, we've got Chris Marvin from Environment and Climate Change Canada. Originally it had been Murray Charlton, if any of you remember Murray. And on the U.S. side, it's Russ Kreis at US EPA. So you have Environment and Climate Change Canada, US EPA, University of Windsor, Ohio State University. I also served for 20 years on the Council of Great Lakes Research Managers, part of the International Joint Commission, and I was the US chair of that group for 6 years. So it's all the Great Lakes. What I'm trying to point out is that the things I'm telling you, this is very much a binational collaborative effort. The targets that we've set were set binationally. I'm the U.S. chair of a task team right now for the latest version of the Great Lakes Water Quality Agreement. 25 scientists, U.S. and Canadian. We used a very simple process when we were coming up with our results and our targets. Everything that we said, when we'd make a decision, we simply did thumbs up, thumbs down, or sideways. And we didn't move forward until we had all thumbs up. There are points throughout our recommendations where I would have liked to see them a little stronger than they are. But if we couldn't get all the thumbs up, we didn't proceed. With that, I'm going to move straight into this, I think. Okay, and I'm going to go pretty fast through this to leave time for questions. This is my hand in front of Stone Lab in 1971. What we're seeing today is exactly what we saw in the 1970s, when Lake Erie was called the Dead Lake. Johnny Carson, 1976, said, "I heard Lake Erie was the place fish go to die." All this got started because of the burning of the Cuyahoga River in 1969, and the way that was covered by Time magazine in the first issue that they had as their environmental issue, and it looked to me like probably half the room have no idea what was going on in 1969. But that particular issue of Time magazine turned out to be the biggest seller ever. So in that issue, you have the burning of the Cuyahoga River, but that's not on the cover. You have the first man walking on the moon in the summer of 1969, but that's not on the cover. And you have a picture of Ted Kennedy on the cover with Mary Jo Kopechne and Martha's Vineyard, if any of you remember that situation. Turned out to be the biggest seller ever, and for our country, U.S., and for the Canadians, it was like we said, okay, we're fed up. Things have just gotten way, way too polluted. The very next year, US EPA is formed, NOAA is formed, and we have the first Earth Day. 2 years later, Trudeau and Nixon in April signed the Great Lakes Water Quality Agreement. What that agreement allowed is, essentially, we put together a group of scientists, US and Canadian, that said, okay, how much do we have to reduce the pollution that's going into the lake to get rid of those images that you saw from my hand in front of the lake in 1971? What do we have to do to solve that problem? The Great Lakes Water Quality Agreement allowed us to do that. It's also important to note that in Ohio, most states, probably the same way in Canada, I'm less certain in Canada, but certainly in Ohio, about 2/3 of our state drains to the Ohio River, about 1/3 drains into Lake Erie. Because of the Great Lakes Water Quality Agreement, the requirements placed on the sewage treatment plants that drain into Lake Erie are much stricter than the requirements placed on the sewage treatment plants that drain into the Ohio River. So in 2015, we had a harmful algal bloom on the Ohio River that went from Wheeling all the way to where the Ohio River runs into the Mississippi, about a little over 650 miles long. Large portion of that bloom, the majority of that bloom, would have been caused by agricultural runoff. But the sewage treatment component was almost equal to agricultural runoff. When we come up to the Lake Erie watershed and we look at the sewage treatment plants that flow into Lake Erie, they are a much smaller percentage of the problem, typically less than 10% of the problem, because they have much stricter requirements placed on them because of the Great Lakes Water Quality Agreement from 1972. In October of that year, we had the Clean Water Act. That gave us the tools to attack the problem. We could regulate sewage treatment plants starting in 1972. Prior to that, we couldn't. Big concern right now in our country is a particular bill that's been introduced, HR 861, that would eliminate US EPA. Back in those days, we were putting in 29,000 metric tons of phosphorus into Lake Erie. US and Canadian scientists, as part of the Great Lakes Water Quality Agreement, put together a target, said we've got to reduce that down to 11,000 metric tons. I'm a young guy in those days. I looked at that. That's a 62% reduction. I said, there's no way we're going to do that. That's just too big. The big advantage that we had in those days is about 2/3, actually more than 2/3, was coming from poor sewage treatment. Typically in those days, we had only primary sewage treatment, which is really just take out the big pieces. Today, about 2/3, or in the case of the Maumee River, about 85% is coming from agricultural runoff. When I'm looking at sewage treatment plants, we could regulate them as part of the Great Lakes Water, as part of the Clean Water Act. In the case of the farmers, we really can't regulate them. And we had about 10 sewage treatment plants that were the primary loaders, even less than that, that were the most significant loaders. And think of the thousands and thousands of farmers that you're dealing with. So it's a very, very different kind of a problem. And the harmful algal blooms are back. This gives you an idea. This is soluble or dissolved reactive phosphorus, DRP. You can see to the left the concentrations in the 70s. That's when we had the big blooms and we were calling Lake Erie a dead lake. The concentration went down to the mid-90s. We're still, when we see the concentrations that you see there in the mid-90s, we're way above what you would have in Lake Huron or Lake Superior, still way above that. But for Lake Erie, that was really good. Unfortunately, since the mid-90s, we've been going back up and the blooms have come back. This is what, up to till 2011, this was the worst bloom that we had ever seen. And this bloom moved out of the western basin into the central basin, east of Peely Point. And essentially, we covered the water intakes for 2.8 million people. And if you look up here where the Thames River comes into Lake St. Clair, you got a harmful algal bloom right up there. That was in October. This is the bloom in front of Stone Lab. This is my hand now. Students always kid me about my arm looking older. I always tell them, but the watch is better. Notice it's a different color. It's simply a different species, but it's still blue-green algae or cyanobacteria. This is the bloom from 2015. Working with NOAA, we came up with a way to rate these blooms, and we rated them 1 to 10. The bloom from 2011 had been a 10, and we expected that to be about the worst that we would see. Unfortunately, 2015, this bloom was a 10.5. This is the worst ever. And again, notice up at Point Peely, and you can see the blooms wrapping around to the eastern side of Point Peely. This is Lake St. Clair at the same time. Obviously, satellite images. To the left, there are lots of different species, different kinds of algae in Lake Erie. When it's really cold, you go out there right now, you'd find a lot of diatoms. In the spring, we tend to get green algae. When things are real warm and we get high concentrations of nutrients, we get blue-greens. And more accurately, they should be called cyanobacteria. I will probably call them blue-greens forever. That's the way I learned it. As our microscopes got better and we could look inside the blue-green cells and we could look at the nucleus, we could see that there was no membrane around the nucleus in blue-green algae. If there's no membrane around the nucleus, then it's not really a true algae. It's actually closer to a bacteria, but it's got chlorophyll, so it would be a cyanobacteria. So if you hear those blue-green algae, cyanobacteria, same thing. Cyanobacteria is actually a more accurate terminology. Anabina on the left is the one that typically blooms in the central basin of the lake. It's a nitrogen fixer. So if nitrogen's in short supply, it can fix its own nitrogen out of the air. Aphanizomenon, that's what my hand was in 1971. Microcystis, that's what my hand was in 2013. Microcystis is what caused the Toledo water crisis in 2014. These cyanobacteria like water above about 60 degrees Fahrenheit, 15.5 Celsius. Phosphorus concentrations have to be high. Nitrogen, it's good if it's high, but if it's low, you'll get species like Anabina that can fix their own nitrogen. You have to give them the phosphorus, but they can make their own nitrogen or get it out of the air. Those preferences tell us where to look. So you look for warm water. So this is going to be primarily a summer problem. Last summer, I spent quite a bit of time up at West Arm by the French River, harmful algal blooms up there, Winnipeg. It's not just an Ohio problem or an Ontario problem. It's not even just a North American problem. This is very much a global issue. Lake Erie sees it. the most because we're the southernmost, shallowest, warmest. I'll show you pictures in a minute. We get the most nutrients, so that's why we see a lot on Lake Erie. These blue-green algae are capable of producing toxins. They don't always produce toxins. They're capable of producing them, and we can determine how bad the bloom is going to be each year by measuring the amount of phosphorus that comes into the lake from 1 March, so we're almost into the phosphorus or the bloom season starting next month, 1 March to the end of July. However much comes in during that period tells us how bad the bloom's going to be. We're worried about these toxins. What I've tried to do here is put most toxic things at the top, least toxic things at the bottom. The 4 that are in red, those are the primary algal toxins. Number 2 on the list, microcystin LR, that was what was in the treated drinking water when they issued the do not drink order for Toledo in 2013. Toledo is about the same population as London. I was coming up here and I noticed that as I came up. So it's about the same kind of a city. About 400,000 people can't drink the water. The second one, or the third one down, the second algal toxin, saxitoxin, that's a terrorism agent. So if these things are in your water and you're going to tell people that it's okay to drink the water, then the amount of those or the concentration that is acceptable is going to have to be really small. US EPA recommends for adults now that the concentration not exceed 1.6 part per billion, and for kids under 6 or 6 and under, 0.3 parts per billion. When Toledo issued the do not drink order, it was about 3.5 parts per billion. The highest concentration I've seen in raw water in the western basin of Lake Erie is about 1,200. The highest that I've seen anywhere was in Grand Lake, St. Mary's in 2010. That is about a third of the way down the state on the west side of Ohio, and they were about 2,200 parts per billion. So why is Lake Erie always at the forefront of this? Well, if you look at the map here, Lake Erie is the southernmost. If you look at it in cross-section, Lake Erie up here, you can see the other lakes. Lake Superior, 1,333 feet deep. The other lakes all over 750 feet deep. Deepest spot in Lake Erie is in the eastern basin here, east of Long Point, right about the border between New York and Ontario. 210 feet. The whole western basin west of Point Pelee is 24 feet. So it's southernmost, shallowest. That should tell you it's going to be the warmest. If we look at the watershed, cut to the chase here, the important things on the Lake Erie situation compared to the other lakes, we have the most agriculture, the most urban, suburban, and the least forest. You put those things together, Lake Erie is going to get more nutrients, more sediments. We're southernmost, we're shallowest, we're warmest, and we get the most nutrients. Then biologically, we have to be the most productive. That's why we're the walleye capital of the world. That's why we produce more fish than the other Great Lakes. Where's our water come from? 80 to 90% of the water comes from the Detroit River. 10% is direct precipitation onto the lake, and 10% is the small tributaries around the lake, the largest of which is the Maumee River at Toledo. Puts in about 3 to 4% of the flow into the lake. So by far, most of our water comes from the upper lakes. So what happens in Lake Michigan, Huron, Superior, up there, that's really important to us, because that's where most of our water is coming from. We don't think, when I think of tributaries, we don't think of the Niagara River or the Detroit River as a tributary. Those are connecting channels. The Detroit River between Lake Huron and Lake Erie, Niagara River between Lake Erie and Lake Ontario. Just now looking at Lake Erie, western basin, very small, 13% of the volume of the whole lake, 5% by area, 5% by area. You've got central basin between Point Pelee and Long Point. Eastern basin, the deepest spot is right about where the B and eastern basin's located. Now look at this very small western basin. 5% of the volume of the lake, 95% of all the water that comes into Lake Erie flows into this really small western basin. So first it's going to tell you that western basin is probably very productive because it's going to have to be the warmest area of the lake, very, very shallow. And in the Western Basin, things are going to happen very, very quickly. And we're incredibly lucky that that's the case. Retention time for water on Lake Erie, 2.6, 2.7 years for the whole lake. Retention time for water on Lake Superior, over 100 years. Retention time for water in the Western Basin, 20 to 50 days. So the problems that we see in the Western Basin, if we can reduce the amount of phosphorus going in, we solve these problems immediately, because that Western Basin flushes very, very rapidly, incredibly important, and we're incredibly lucky that it's that case. If we caused these same problems on Lake Superior or on Lake Michigan, take over 100 years easily to solve them. That's why it's very important that we understand, we come up with these solutions on Lake Erie, but then we transfer those solutions all over the world. And when I talk about Grand Lake St. Mary's in Ohio is a much, much bigger problem because it has a very long flush out rate. Retention time for water is high, so it's going to be a big problem for many years to come. 50 and 2 rule. This gives you an idea, just a comparison now between Lake Superior and Lake Erie. In the Great Lakes, those are the two extremes, the two most different lakes. Lake Superior, very big, very cold, very sterile, not many nutrients. Lake Erie, warm, shallow, lots of nutrients. So 50 and 2 rule, it's my own. You won't find this in a book anywhere. It's not exact, but it's close. It's instructive. Lake Superior's got 50% of the water in all the Great Lakes, but only 2% of the fish. Lake Erie's got 2% of the water and 50% of the fish. Every year, Lake Erie will produce more fish than any of the other Great Lakes, and many times it produces more fish than the other 4 combined, and it has only 2% of the water. But it's possible to have too much of a good thing. You put in too many nutrients, and you get too much algae and the wrong kinds of algae. Eastern basin of the lake, we get large concentrations of Cladophora, not a harmful form of algae, a nuisance form of algae. Doesn't produce toxins, but it tends to roll up on the beaches up here on the North Shore and along the shoreline, creates problems up there. Flies, you get anaerobic conditions within the decaying algae. Flies breed in that. The maggots get eaten by ducks, and you have botulism problems. So those are the 3 issues that you typically get, and Lake Erie has all 3 of them. Those are what we're focused on right now in solving US and Canada. We focus on limiting phosphorus. This is what we did in the 70s. It's what we're trying to do again right now. It's the best strategy ecologically and economically. Reducing both phosphorus and nitrogen that's clearly the best thing to do. That's what we should be trying. But you can solve the problem by reducing only phosphorus. You can't solve it by reducing only nitrogen. We're learning a lot more about how important nitrogen is. We can actually make the blooms. We can have a harmful algal bloom, but remember when I said they're capable of producing toxins? We can make them less toxic by giving them less nitrogen, because the toxin that they produce, that microcystin, is 14% nitrogen by weight. So you give it less nitrogen, you can have a bloom, but it can't produce toxins. Reducing both nitrogen and phosphorus is clearly the best thing to do. Okay, let's talk about some general things about where the phosphorus is coming from. Sewage treatment plants, back in the 70s, big source. Sewage treatment plants have all gotten much, much better. And when you think about it, sewage discharges don't vary much from year to year. Very minor amount of variation. Whereas, or think of it a different way, I don't think there's anyone in here that flushes their toilet more when it's raining than when it's not raining. In the case of agricultural runoff, when it's not raining, you're not getting any agricultural runoff. So you have a drought year like 2012, very little agricultural runoff. Sewage treatment load is the same in 2012 as it was, say, in 2011, which was a very, very wet year. Or you look at 2015, very, very wet year. Huge load comes in from agriculture, The sewage treatment load is about the same. You look at 2016, again, a dry year, the load from agriculture is very low. The sewage treatment load is about the same. That's the way that works. The vast majority, 80 to 90% of the load comes in when it rains. We know this. We're very fortunate. Heidelberg University in Tiffin, Ohio, has monitored the Maumee River, the Portage River, and the Sandusky River every 8 hours, 365 days a year for over 40 years. We know what comes in out of those rivers, when it comes in, and we know how that is impacted. We have situations where we could see in October, things had been wet. We had about a 2-week dry period. Farmers all got out, spread their fertilizer, and then we hit a real wet spell, and we can pick up the huge spikes in phosphorus going in. We know what causes this, when it's coming in, and we're going to have, starting this year, we're going to have that same quality data for the Thames River in Canada. So we know most of it comes in when it's raining. Now think of what's happened to our rainfall events over the last 50 years. Number of storm events per year, up 67%. When I'm talking storm events now, these are typically the storms that produce more than 2 inches of rain in a 24-hour period. Number of spring runoff events up 40%. Number of annual storm discharge up 53%. And 80 to 90% of the load comes in during those storm events. So climate change is one of the things that's driving this. This is probably an image that not many of you have seen. The pink or magenta bars on here represent the amount of phosphorus that comes in out of tributaries. And I've got about the top 90 tributaries around the Great Lakes on here. The green bars are what is coming in from the connecting channels. So I'll just highlight a couple things here. And this is 2008. We used 2008 as our base year in that it wasn't the wettest spring, but it was a pretty wet year. In fact, if we look at about the last 20 years, we only get years wetter than 2008 about 10% of the time. That's really important, because if we could then reduce the load in 2008 down to some acceptable level, we could then say, okay, if we can do it in 2008 and we have best management and practices in place that will reduce the 2008 load to an acceptable level, then we ought to be able to produce acceptable results 90% of the time, or 9 years out of 10. This is the way our team of scientists, US and Canadian scientists, work. Okay, now think about things I've told you so far. Detroit River in 2008 put in about 2,000 tons of phosphorus. Remember, the Detroit River brings in 80 to 90% of the flow? The Maumee River put in 3,800 tons of phosphorus, brings in 3 to 4% of the flow. The next biggest loader is the Sandusky River. The Sandusky River, size-wise, watershed-wise, is pretty similar to the Thames. It brings in about 1,100 tons. This particular year, we estimated that Thames brought in, this is about 300 tons, but what we're finding on the Thames, or 235, what we're finding on the Thames is that the load out of the Thames is often up around 800 tons. We'll get much better data starting this year on the Thames, but the Thames and the Sydenham and the Grand over here into the Eastern Basin, those would be the ones that we're most concerned about on the Canadian side. The Sydenham's, depending on how much rain you get, when it comes in, the Sydenham put in over 300 tons. Thames puts in over 800 tons. You go over here to Green Bay, about 650 tons. Saginaw Bay, about 500 tons. Harmful algal blooms in Green Bay, harmful algal blooms in Saginaw Bay, harmful algal blooms Western Basin, harmful algal blooms in Lake St. Clair. Get an idea that it tells you where these problems are likely to occur, and it's primarily your tributaries that are in heavily agricultural areas. Now, Cuyahoga River, notable from 1969 burning. That was actually the 5th time the river had burned, but that was the one that was covered by Time magazine. Urban tributary, Cleveland is located there. It's has a history of pollution problems, but it's a relatively small impact on the lake because it's a small river. So you think of the Maumee putting in 3,800 tons, the Detroit putting in 2,000 tons. You got Cleveland down here, and the Cuyahoga puts in 450 tons. Not the cause. So we've got to be working in this western basin, the agricultural land in Michigan, Indiana, and Ohio, and then agricultural land up here in Ontario. We need to get better information, better loading data, we really do, on the Grand. But those are your most significant tributaries, and none of them come close to the Maumee, which is why our biggest focus is in Ohio. Typically, the vast majority of this phosphorus is coming from the U.S. side, not the Canadian side. Okay, let's talk about phosphorus for a second. In the 70s, we were focused on total phosphorus. Total phosphorus is particulate phosphorus, the phosphorus attached to sediment particles, and the dissolved phosphorus, or you'll often hear it called DRP, dissolved reactive phosphorus. The particulate phosphorus is about 25% bioavailable. The DRP, 100% bioavailable. The DRP, that loading, that increase in DRP is what's causing these blooms. Because overall, when we look at total phosphorus, looking back over the last 50 years, the increase in total phosphorus coming into the lake is only up about 13%. The increase in dissolved reactive phosphorus coming into the lake is up 150%. So we need more best management practices that are focused on that DRP. Historically, our best management practices have focused on the particulate phosphorus. Think of the things that we've done. We've tried to prevent erosion. Why do we do that stuff? When I took agronomy, I bet you this is the case with 99% of the people that have some kind of an agricultural education, and they took agronomy. When I took agronomy in 1970, I was taught that phosphorus will attach to sediment particles and come off the surface. Nitrogen will dissolve in the water and come out through the tiles under the field. We now know that the DRP, over 50% of the DRP leaving a farm is coming out through the tiles. Okay? In the Maumee River, we have 800,000 miles of tiling. That's a big piece of the problem. I saw a lot of fields on my way up here from Windsor on the 401, new tiles coming in on these fields, and you're probably experiencing the same thing. Years ago, we would have had tiles maybe 50 feet apart, then 30 feet apart. Now we're seeing tiles 16 feet apart, getting closer and closer together, more and more tiling, and the dissolved reactive phosphorus is coming out through those tiles. Also coming off the surface, but a big portion of it coming out through the tiles. So you got more rain, got more tile, another source of the problem. Plus, think of the fertilizers that we're putting on now. All of you don't want to put on particulate. Would you want the phosphorus you put on your field to be only 25% available? You're trying to put on phosphorus that dissolves quickly so your crops can use it. So the phosphorus we're applying is very much in the DRP range. That's what we're putting on. So we need to come up with best management practices that are focused on that rather than on preventing soil loss and erosion. Soil loss and erosion is still very important, but recognize that you know, 1 ton of DRP is equal to 4 tons. You'd have to remove 4 tons of the particulate phosphorus to have the same impact as 1 ton of the DRP. All right. Got to go a little faster here. I'm going to show you three charts. They're all similar. This one is discharge out of the Maumee River. It's for a water year. Water years are October 1 to September 30th. That's the U.S. fiscal year. One thing I've learned on the Canadians in working with IJC, for Ohio State, I have to do all my reports based on the state fiscal year, which starts July 1. For Canada, I have to do all my reports based on, I think it starts April 1. For the U.S. government, I have to start everything October 1st. And for all of our donors, we have to start everything January 1st. So basically, I'm doing nothing but reporting and just simply changing the date. In any event, green line here, that's how much water came out of the Maumee River from the beginning of March to the beginning of August or the end of July in 2015. So you see that it was wet in the beginning of March, and then at the beginning of April it dried up, and then it got wet again from, say, the beginning of May up until the beginning of June, and then it was dry. Okay, that's 2011. 2012, drought year. I'm sure it was a drought year up here also. This is the load that went in 2012. So you got about 5 times as much water went out of the Maumee River in 2011 in the spring than in 2012. Huge difference in those 2 years. 2015, the amount of water out of the Maumee, even higher than 2011. Remember 2015, the bloom was worse? Think about the timing on this and how it impacts agriculture. In 2011, all the rain came prior to June 1st. In Ohio, we couldn't get crops in the field until it was June before we were getting stuff planted. In 2015, all the rain came starting June 1st. Crops were in the field, things were growing. Think how that would impact. 2011, you would expect to see a lot of sediment entering because you don't have, all this rain comes before you have a growing crop. 2015, the rain comes after the crop's in the field, it's growing. So you'd expect to see more sediment entering the lake, more particulate phosphorus entering the lake in 2011 than 2015. This is 2016, this is last year. Okay, so let's see what particulate phosphorus looks like. This is total phosphorus, so this would be sort of heavily particulate here. You see 2011, way up here. Huge amount of particulate phosphorus. 2015, lower, okay? Simply because of the timing of the rain. Now I'm going to do a switch and go over to DRP. The thing that drove the bloom that made it the worst bloom ever in 2015 was the timing of that bloom, and we had more DRP, more dissolved phosphorus. The crops were in the field, they were growing. So when we were getting the runoff, that runoff was not coming off the surface carrying lots of particles with it. It was going down, entering the tiles, and we're getting a huge amount of DRP coming off. In all cases, you see 2012 way down here, 2015 or 2016 right here, gives you an idea of what you would expect. You'd expect to have really bad blooms in 2011. You'd expect the bloom in 2015 to be worse. It was. You'd expect the bloom in 2012 to be really low. It was. You'd expect 2016 to be a little higher than 2012. It was. That's the way the model works. It's literally that simple. Okay, so these are all the blooms. Black indicates no bloom. Red means a really high concentration of the algae. the yellow a little bit less, the green even less, blues less, and you get into the blacks, no blue-greens. We can do this from satellite because the blue-green algae have a pigment, phycocyanin, that none of the other algae have. So all we have to do is look for that wavelength of light from our satellites. We can pick up the phycocyanin. The more phycocyanin you see, the more blue-green algae you see. It's that simple. So you can see simple things based on what we've already talked about. The giant bloom from 2011, huge amount of phosphorus went in because it was a really, really wet year. 2012 was the drought year, very, very little phosphorus. Remember, Western Basin, very small, things happen rapidly, retention time for water 20 to 50 days. So if we reduce the amount of phosphorus going in, the problem goes away immediately. Here's your evidence. 2011 and 2012 shows you that that's the case. 2015 and 2016 demonstrates it again. Bloom from 2015, now the biggest ever, even a little bigger than this one based on the density of the algae. This is the bloom from 2016. Great reduction in the amount of phosphorus. The bloom from 2014, when Toledo had the water crisis, that was a crazy event. The amount of press coverage, my phone did not stop ringing. But when they first called, when US EPA and Ohio EPA called and we were working on this problem, they called out to Stone Lab, and we didn't have a bloom at all at Stone Laboratory when Toledo had the water crisis. These are floating forms of algae. You get a northeast wind, blows the algae to the Toledo area, mixes it because of wave action, down to the water intakes, they suck in the harmful forms of algae, shut down the plant. And we had no bloom out at Stone Lab at that time. Okay, our objectives for the work that I'm working on right now with the Great Lakes Water Quality Agreement. They've told us to do science-based objectives, focus on harmful algal blooms, Western Basin, Hypoxia, Central Basin, Cladophora, Eastern Basin. I'll tell you right now, we've come up with really good targets for harmful algal blooms, for hypoxia, but we have not yet come up with what we would call a science-based target for Cladophora. Our science is simply not good enough to essentially get all the thumbs up in the room. That's where we are on that one. On the other two, we can. Adaptive management, both countries have agreed to this. It means we're going to set a target. We're going to evaluate carefully as we come down. If it turns out that target is too high or too low, we'll adjust accordingly. We're not going to pick a fixed target. We want to make sure that we're producing the desired results. We've identified 14 priority tributaries that are the big tributaries that are putting in most of the phosphorus, or they're tributaries where we can identify a harmful algal bloom at the mouth of that tributary where it comes into the lake. For harmful algal blooms, we're calling for a 40% reduction in the amount of phosphorus that goes in. Remember in 1971, it was a 62% reduction, what we had to do back in the 70s. Today it's a 40%. And our goal is to produce blooms that look like 2012 or smaller 9 years out of 10. 1 year out of 10, we're going to produce blooms that are greater than that because we no longer are confident that we can predict how much rainfall we're going to get. Climate change, and because of climate change, we may also see blooms that are worse than 2012 more frequently than 1 year out of 10. Our models just are not good enough in that area yet. For hypoxia, or the dead zone, the cold bottom layer, that case we need to reduce the annual load. So it's not the spring load that causes anoxia, it's the annual load. Fortunately, the amount is the same. What this looks like, in the 70s, we came up with a target for total phosphorus coming into Lake Erie of 11,000 metric tons. The new target for Lake Erie is a little under 7,000 metric tons. This shows you the size of the blooms. From 2002 to 2016, the shaded or sort of dimly marked, that's the size, the actual size of the bloom. The dark green sections that you see here, that's how big the bloom would have been if we had best management practices in place that would reduce the load by 40%. So think about it. 2008, here's the bloom of 2008. If we reduce that bloom by 40%, we come up with a bloom that looks like this, which was about the same size as the 2012 bloom. That's our goal. So we'd like to have blooms about this size down in this area. We'd also be acceptable. Here's 2012. 2016 wasn't too far off. 2004, right on. All the other ones were over. But if we had been successful, if we had the best management practices in place, we would have only exceeded our target in 2011 and 2015. And even then, those blooms would have been much smaller than they actually were. So you can see that we're not trying to totally eliminate the blooms. We're trying to come up with something that we think that society would find acceptable. Another way of looking at this is what the bloom of 2008 actually looked like. Here's the bloom from 2011. Here's the bloom from 2012. A 40% reduction makes the bloom from 2008 look like 2012. Makes the bloom from 2011 look like 2008. And it makes the bloom from 2012 go away. And what we'd like to have is blooms like this one or smaller 9 years out of 10. This is the lab again. In there just to show we're a lot of work right now at the lab. Every year we're doing a lot of workshops for water treatment plant operators, teaching them how to identify the harmful forms of algae and how to remove the toxins. Okay, where are we philosophically on this? I like to say right now we're fighting the third battle of Lake Erie. We fought the first one, 1813, U.S. against the British. Second one, 1971. Now we've got U.S. and the Canadians working together, and we solved it. We took Lake Erie and made it, instead of being the poster child for pollution problems, we made it the walleye capital of the world, and we made it the best example in the world of ecosystem recovery. Right now, we're in the middle of the third battle of Lake Erie. Let's talk about the impact. Is this worth doing? As a result of reducing the phosphorus load in the 70s, making Lake Erie the walleye capital of the world, charter fishing businesses, these are just Ohio data now, but 40% of all the charter boats on the Great Lakes are in Ohio. Individual businesses went from 34 to over 1,200. Coastal businesses along the shoreline went from 207 to over 425. The walleye harvest went from 112,000 fish to over 5 million fish. Became the walleye capital of the world. Again, best example in the world of ecosystem recovery. 8 counties in Ohio that border Lake Erie. There's 88 counties in the state. The 8 that border Lake Erie, related to tourism, employ 120,000 people and produce about $13 billion worth of economic impact. So we often hear things that, do you want a good economy, do you want jobs, or do you want a healthy environment? And you can have both of those things. What we're trying to do right now is to keep agricultural production high, but also keep the phosphorus on the fields. What we've got right now in the third battle, the blooms came back in 2002. The bloom of 2011 covered the water intakes for 2.8 million people. We had multiple blooms in the Central Basin in 2012. In September of 2013, 2,000 people over by Davis-Besse were told not to drink the water because of harmful algal blooms. In 2014, 400,000 people were told not to drink the water. We've had many health impacts statewide on this. Many dogs have been killed because of this. Charter fishing down 25%. So that's sort of where things stand right now. Conclusions, things for all of you to think about. DRP dissolves in the water and comes out of the tiles. So we're doing things like, let's try to hold the water back in the tiles. There are times that you're going to want to let it out, but we can also enhance production by holding it back. Some of you may know Larry Brown's work from over at Ohio State. If you can control the water level in your fields, you can actually increase your production and you can keep the DRP present. Phosphorus loss is directly related to the amount of phosphorus on the field. So the key thing here is don't put too much phosphorus on. Good news, when we look at the Maumee, we have target concentrations of phosphorus that we'd like to see, flow-weighted mean phosphorus concentrations coming out of the Maumee River. When we measure the amount coming out of the tiles, we meet those targets when we don't apply too much phosphorus. What that also tells you, it tells you that you can get maximum crop production, but we can meet the targets for of phosphorus coming out of the tiles. But it also tells us that we probably can't apply multiple years of phosphorus at the same time. Or we're going to have to come up with BMPs that in some way are going to hold that phosphorus if we apply multiple years, and that's a big challenge. And I see in Michigan, for example, right now, farmers being allowed to apply 4 years worth of manure in one application. There's no way we're going to solve the problem if we keep doing that. We also know that essentially you can't bank it. And back when I took agronomy in the 70s, that's what I was taught. Because we were concerned, if we could prevent erosion, we could bank our phosphorus. I bet you there's a lot of people in here that were told exactly that you can bank your phosphorus. You really can't. We also know that legacy fields are a big part of the problem. You get fields that have way too much phosphorus on them, they're going to bleed too much phosphorus for many years, even if we don't put more on. 60%, we can reduce the amount of phosphorus coming off the surface by 60% if we incorporate in some way, rather than simply broadcast application. On the Maumee River, 42% of the acres are responsible for 78% of the phosphorus. 42% of the acres are applying phosphorus at above removal rates. 1% of the acres are responsible for 40% of the sediment loss. When we do social science research with the farmers, we see that 1/3 of the farmers probably already doing the right things. 1/3 of the farmers are, we believe, based on their responses and the conversations that we're having with them, they're going to do the right things. They needed more information. Now they're making the decisions. We think they're going to do the right things. But we're left with that last third of the farmers that I use the term aggressive encouragement. It's going to take something else to get them to do it, and that's a big concern. Things we know, total elimination. If we totally eliminated all the point sources, the load goes down by about 9%. So it's not point sources, it's not sewage treatment. Models show that it is possible to achieve the 40% reduction and keep ag production high, but we're going to have to change practices, and it's probably not going to happen only voluntarily. In my opinion, what we're going to need is more farmers taking voluntary action, more people being innovative and trying new things and sharing good results with other farmers, more targeted incentives. What can we do to reduce the risk for farmers? And then more common sense regulations. In Ohio, we've had Senate Bill 150. Essentially was an education. You take the CCAs, and we want to make sure everybody gets the right training, so we're telling farmers the right thing. Everybody knows this information, knows how to do it. Senate Bill 1, common sense regulations. Don't broadcast application onto frozen ground. Don't put manure on snow. these are common sense things. You can't do those things any longer. And then recommendations now are follow what they call the 4 R's: right amount, right time, right place, right form. A lot of farmers are asking me right now, why is that optional? And I don't have a good answer for that. But that's where we are right now. And with that, I will stop and take maybe a question or two. I've gone over my time, I think.
Do we have any questions on the cards from the audience? Got a couple at the back there we'll grab. Here's a good question for you right off the start. What is the single most important practice that farmers could do to mitigate phosphorus load that does not adversely affect farm production?
I'll give you 2, because I think, honestly, I think we could solve the problem if we could get everyone to soil test and not apply more phosphorus than is needed, and to incorporate the phosphorus when they apply it. If everybody did that, the problem goes away. It's just that simple.
Lots of questions here. Okay, how was the 1970s crisis corrected? What changes were made?
Big thing in the 19...
This is a question from someone obviously born after that date.
The big changes in the 70s were, in those days, again, the vast majority of the phosphorus was coming in from, I said poor sewage treatment. Think of it as incredibly poor sewage treatment. It was just really, really bad. And so the big changes in those days were federal funding and state funding and taxes on people to greatly improve our sewage treatment plants. And I would argue again that it was a larger amount of phosphorus we had to reduce, but you could focus on a handful of sewage treatment plants and solve the problem. This is a much different and I would say a bigger challenge today, because the vast majority of it now is coming from agricultural production, which is, you can't regulate the same way you can a sewage treatment plant, and there are just so many farmers. And we don't want to see the number of farmers go down.
Okay, and I'm sorry for the people whose questions I didn't get to ask. I'm going to ask you one final question in the interest of time and keeping us on time. How does the legacy phosphorus in sediment in the lake affect your testing data? How does legacy phosphorus in the sediment in the lake affect your testing data?
Great question. When we think of legacy phosphorus, I talked about the legacy phosphorus on an agricultural field. But do you remember the chart that I showed with the 90 tributaries and how much phosphorus was coming in? And I also showed the amount of phosphorus coming in from the Detroit River and the amount of phosphorus going out of the Niagara River. And if you were doing math on that and thinking about it, that particular image shows you how a wetland works. And Lake Erie is like a giant wetland for Lake Ontario. We had 2,000 tons of phosphorus coming in at the Detroit River. We had 2,000 tons of phosphorus going out at the Niagara River. But we had 3,800 tons of phosphorus coming in from the Maumee, 1,100 tons of phosphorus coming in from the Sandusky, 452 tons of phosphorus coming in from the Cuyahoga, 450-something coming in from the Canadian Grand. Bottom line is there's about 9,000 tons of phosphorus that comes into Lake Erie and doesn't go out. In the Western Basin, that legacy phosphorus in the sediment, buried in the sediment, has a small impact. It gradually moves because of wave action, average depth 24 feet, so the western basin stirs up easily, and the sediment moves to the central basin. Gets to the central basin of the lake, and it's deposited in the central basin. And it takes a storm like Hurricane Sandy to lift up the sediment in the central basin and move it into the eastern basin. So pretty much the central basin is a big sink for this phosphorus. The reason they've charged us with reducing hypoxia, or that dead zone, when that cold bottom layer becomes anoxic or without oxygen during the summer, then it changes from an oxidizing environment to a reducing environment. What that means is that all the phosphorus that is buried down in the sediment redissolves into the water, along with heavy metals. When that cold bottom layer sloshes up over water intakes for Cleveland, the city of Cleveland sucks in all of that really nasty water. Causes health issues, clearly taste and odor issues, much more expensive to treat. But when the thermocline that separates the warm surface layer from the cold bottom layer, in the fall, as the warm surface layer cools and equals the temperature of the cold bottom layer, the thermocline disappears. When that happens, all that phosphorus that has redissolved into that cold bottom layer is released back into the lake. So now you're seeing impact of legacy phosphorus. I think of legacy phosphorus in Lake Erie as our paying for our past sins. That's essentially what we're doing. And I also love to take, if any of you, if your group would ever like to come up to Stone Lab and go out on our research vessels, I love taking farmers out on the Western Basin and dropping an Ekman dredge down and picking up a bottom of Lake Erie and telling them that there's no such thing as soil loss. I know exactly where it is.
Thank you very much. I have one simple question before we thank our speaker. When they're going out on this trip with you, can they bring a fishing pole? That's the only question I have. Okay. Thank you very much for a great presentation. We're going to try and get ourselves a bit closer to being back on time here, and I apologize. Off the start, we had a faux pas for this group, and that is we did not start exactly on time.